Okay, so welcome everybody. I'm Terboven from RWTH Aachen University in Germany. I'm with the OpenMP Language Committee since 2006, and today I'm going to talk about OpenMP tasking. And I wanted to do this talk together with Michael Klemm from Intel, but he's not available. But what we created together is a slide deck that will cover pretty much everything of OpenMP tasking to give you a pretty good overview, including the new features in OpenMP 4.5. So I want to start with a very nice and hopefully motivating example, and we are serious computer scientists. So what we deal with are important algorithms like solving Sudokus. And then I will take a look at scheduling, dependencies, and some minor tasking clauses that are new in OpenMP and that intend to show you how powerful this feature actually is. So let's take a look at Sudoku. And I'm not trying to come up with a very efficient algorithm here. I'm trying to parallelize an algorithm that's rather easy, just to show you how to use the OpenMP tasking concept here. So I'm assuming you're aware with Sudoku puzzles and simple algorithm that finds all possible solutions, but is not efficient because it revisits many configurations is the following. We have to start at an empty field, insert a number, check the Sudoku. If it's invalid, delete the new number, or delete the number, insert a new number. In the other case, if it's valid, we have to go to the next field. If we do this, and it's a recursive algorithm, we will find all possible solutions, as I said. And if you take a look at this algorithm, it's kind of irregular. So there's not a big loop that you could use any for work sharing construct with. Or if you think of the sections work sharing construct in OpenMP, you really have a problem because it has a very depth or very high recursive depths. So you would have to deal with a large number of threads being created. And this is where tasking comes into play. So what are tasks? Tasks are small pieces of code that you define in your actual program. So it's basically the structured block that's contained within the task construct. And tasks also have some data associated with it. So we have the OpenMP data scoping clauses that you're probably familiar with, like shared, private, first private, and of course a default clause. And with that, you can manage which data is contained inside the task and what is actually shared data that's available as a reference. So all the tasks that you're going to express in your program are independent from all the other tasks. And this kind of recursive definition of a task actually can teach you that these are very small scale, or that's a very fine-grained way of expressing parallelism. So tasks do not come with the restrictions of the work sharing constructs, like that you can't allow that you're not allowed to nest them into each other. Instead, tasks can be nested inside other tasks, inside work sharing constructs, or just inside the parallel regions. And actually, as we will see in a second, you will be able to express your parallel program in terms of millions and millions of tasks, really millions. And the OpenMP runtime will take this large amount of tasks and map it to the team of threads that's available to perform the parallel work. So whenever the OpenMP runtime encounters a task, or when the program flow encounters a task, the runtime has two options. It can either execute the task directly, or it can put it onto a work queue. And all the threads that are waiting for whatever reason, for example in the barrier or any other synchronization construct, they will monitor the work queue and pick up the task for execution. And that's exactly where I said the runtime has the freedom to map these millions and millions of tasks to the team of threads. And there's a lot of cleverness involved. So if you have too many tasks on the work queue, you might waste memory. If you have too few tasks on the work queue, you cannot guarantee that all the cores and threads will be kept busy. So take a, we have also some, synchronization constructs that play along with tasks. So you might know the barrier. As I said, when threads waiting there, they can pick up tasks that are ready for the execution. And when the barrier has been passed, it's guaranteed that all threads have reached the barrier and that all tasks have been completed. Only task-specific synchronization construct is a task wait. It doesn't wait for all tasks. It only waits for direct child tasks of the thread or tasks that encounters the task wait. So in the recursion level, as I said, we will only wait with the task wait construct for the direct childs. Childs of these direct childs will not be waited for in the task wait. And this is why recursive parallelism in OpenMP tasking does work. So now let's take a look at how we are going to parallelize the Sudoku solver with OpenMP tasks. The first construct, and I will show a larger excerpt of the code later on, the first construct here is a parallel and a single. That sounds strange, but that's exactly what I need. I need a parallel construct in order to create a team of thread. And then I need a single, so that only one thread starts the execution of my algorithm. Because if we take a look at over here, we have to start searching for one empty field. And I want only one thread to start the execution of the algorithm. And later on in the recursion steps, we're going to express more and more tasks to finally come up with a parallel program. So we run with this one thread through the algorithm. The others jump around the single, wait at the implied barrier, and hence are available to execute any task that's inserted, added to the work queue. So we finally will arrive at this step 4 in the algorithm, and this is actually where we have the parallelism. If the number doesn't fit, so that means if the Sudoku would be invalid, we can express a parallelism that all the other possible numbers can be tried out in parallel. And we create one task for every possible other number. In that, we have to create a copy of the Sudoku board because we are, as I said, going to revisit a few configurations when we do a simple algorithm like that. And finally, at the very end, we have to wait for our child tasks. And this is how it looks like in actual OpenMP code. If you're interested in the full Sudoku solver, just send me an email and I will reply with the code. It's actually not really long. So here's a parallel single, and that only consists of the code of the one call to start the recursive algorithms. All the other threads, as I said, will jump around and wait at the end of the barrier before the parallel and will just work on the tasks that are enqueued into the task queue. The solved parallel is a recursive algorithm, and the sketch of the code is shown on the next slide. What you will also find in some OpenMP tasking benchmarks is something like the following: OpenMP parallel sections. That's syntactic sugar. So sections, that's a very static construct, and all the sections that will follow here are executed by individual threads. Here in this very simple example, we have only one thread, and that means one thread will start the execution with solved parallel, the others will jump around. And that's basically equivalent to the parallel single, but parallel single is not a construct, are not constructs that can be combined. And that's the actual implementation then. So for e equals 1 to the field size, that's actually the number, the possible numbers that we're going to evaluate. And we do the pragma-OP task first private here because we want to capture the values of I, X, and Y. These are the positions in the field and the actual pointer to a field inside the task. And first private is really important in the context of task because the task here will be created and can be put onto the work queue, and when it's later taken out from the work queue and brought to execution on the thread, the values of the surrounding variables might have been changed. And the task obviously needs access to all the values as you intended. So first private will create new private variables of the given names inside the task. But as with parallel, first private means it will capture the value of these variables I, X, Y, and Sudoku and copy them into the task. And when the task finally will be picked up from the work queue, we can create a new Sudoku board with a copy constructor here, set the current number, at the position, and continue with our parallel search. Okay? First private is for all private variables in the enclosing construct of tasks, the default, so with the intent to make many programs safe and ensure that all the necessary values are copied inside the task. I implemented that, and that's a performance which I got. So it's a 2-socket Intel Sandy Bridge machine with 8 physical cores per socket. With hyper-threading and 2 sockets, we come up to 32 logical cores. And the total speed up, this is this grayish line here, maxes out at 3.6. Is that good? I was pretty disappointed. But what we are encountering here is a very important performance problem pattern that you will find in all task parallel programming models. So we looked at this code with different tools. On the left-hand side, you will find an output of the Scalaska tool using Scopee-based analysis. On the right-hand side, you will find something from a tool named WAMP here. So Scalaska gives us some statistics. And what we're doing here is we execute in total 1.3 million tasks. And if we divide that by the program runtime of about 5.7 seconds in the serial case, the average duration of every task is only 4.4 microseconds. And the problem here is, of course, that there's some overhead of creating the task, putting it onto a work queue, taking it back for execution. That's some overhead, and if the task is too small, it doesn't pay off. So with every small task, we're only adding overhead. And you can see that in the recursion level, at some point, we still have pretty costly tasks. So at this recursion level 6, the average duration of a task is still 0.167 seconds. When we go down deeper in the recursion tree, we go down to 2.2 microseconds. So the pattern to solve this problem is the so-called cutoff. At some point, when we have created a sufficient amount of tasks, we have to stop creating more tasks. There's a clause for that in OpenMP, the if clause, which I will show on the next slide. And if we do that, so the if clause will solve the problem here, we come up with a speed up that's shown at the black line. So we have a linear scalability with a number of physical cores in the machine. So when we have enough tasks, we stop the creation of more tasks and let the threads continue the task so that we save the overhead. And the good rule of thumb is to create about 10 times the number of tasks that you have as the number of threads or cores in your machine. So tasking can be made successful with this important performance problem pattern. So the if clause can be put onto a task. It takes an expression, and if the expression evaluates to false, that will mean that the task is directly executed, and we save the overhead of putting a task onto a work queue and taking it back later on. So it's kind of sequential embedding into the enclosing task. A few more words on scheduling and task dependencies. So tasks, once created, will always be executed by the same thread which started the execution. We differentiate between the creator and the executor. The creator thread is the one that encounters a task construct in the actual code, creates a work package, puts it onto the work queue, and then the executor thread is the first one which picks up the task from the queue, brings it to execution. The execution of a task might be interrupted at, for example, the encountering of an inner task construct or any other of these task scheduling points, as we call them. But in a standard case, the executor thread will always come back and complete the task. If you don't want that, you can put the untied clause, and that means tasks are not tied anymore. So if a task has one executor thread and is interrupted, a different thread might come and pick it up. So that would give the implementation more freedom to perform a better load balancing among the task. And if you want to further improve the load balancing, we have the task yield clause. I will just jump to an example here. So what we do is we have a function called something useful and something critical, and we create a number of tasks in this simple example. So we assume something useful performs some computation, and then we want to store the result within something critical. So we are going to modify some shared space here. And if we are going to modify this shared data, we have to guard it with lock routines here. And if multiple threads will do the same, only one can acquire the lock. I'm assuming you're familiar with locks in this case. So what we can do is, if we don't get the lock, we will instruct the runtime to put the current task to sleep so that the runtime can take the thread that was executing the task and put a different work on that particular thread, for example, a different task. And later, when that task is being picked up again, it might have a better chance to acquire the lock. So this may improve the load balancing in OpenMP runtimes. We have more synchronization constructs, a task group construct, for example. The task group is, again, a structured block, and at the very end, it contains a task barrier which waits for all the tasks that are created within this task group construct. And with that, it complements the barrier and the task wait to offer all kinds of task-related synchronization that are well known or used described in the literature. And in OpenMP, we have task dependencies. That's a feature of OpenMP 4. So with that, you can express that the task has to wait for some other task to be executed first. And we introduced the feature in a way that you can express the actual data flow. We have two types of dependencies. We have in, and the in and out dependencies are equivalent. So in means The, the generated task will be dependent on the previously generated sibling task that references a data value in the in or in-out clause, and out will mean it waits for in, out, and in-out clause. And I have an example here to illustrate that. So we have again the parallel single pattern, which creates one thread that starts the execution here. It will loop over several iterations of this I loop here, and it will create one task which I call T1 that does some pre-processing of the data. It has an out dependence into the variable x, and then we have tasks T2 and T3, which are siblings of this task, but they have independencies on the variable x. And that means first T1 has to be completed before T2 and T3 can be started, but T2 and P3 can then be executed in parallel. Okay, and yeah, that's what I just said. And this can be actually used to express real dependencies. That's an example from linear algebra domain. Actually, BSc implemented that, and they explored this concept with the OMS parallel programming paradigm. And I think on the next slide, there's a proof. Jack Dongara shared the OpenMP tasking construct. So previously, with their linear algebra stuff, they used their very own implementation of tasks, and now they're considering OpenMP 4 and 4.5 implementations to relieve them from the burden to do their own stuff. They consider our feature stable enough. Before I close, I want to briefly run through the new construct that we have in OpenMP 4.5. The task loop construct is very similar to the work sharing construct. It parallelizes over the iterations of a loop, but instead of distributing the work between the threads in the parallel team, it creates tasks. And that comes with all the advantages of tasks. So tasks can be nested. They give the runtime more freedom to do load balancing and stuff like that. There are some clauses with it, but basically these most of the clauses are the one that you know from the for work sharing construct with respect to the data scoping. Two clauses are special. You can either specify the grain size, the number of iterations to be grouped per task, or the number of tasks that should be created by the construct. So that's a new 4.5 feature. We also introduced priorities, and that's basically a hint to the runtime that two tasks which are ready, and if two tasks are ready and they have priorities, the runtime will pick the thread with a higher priority first. It's meant as a hint. It's not a feature that you can rely on to enforce a certain requirement. But again, if you have very complex dependencies and an algorithm in which you can actually guide the runtime to come up with a clever scheduling, priorities can be used to express it and to achieve better performance. If you don't specify it, all tasks are of the same priority, which is a value 0, as we have it today. And then in my Sudoku example, I already said at some point we might have to stop the creation of more tasks. We have final and mergeable. Final takes an a Boolean expression. If it evaluates to true, the runtime will be notified that this is a final task which will not create any further task, and this again allows the runtime to perform certain performance improvements. For example, to merge the data environment of the final task with the enclosing data environment. But it's a dangerous feature, so here you see a difference. First, private would copy, in case it's a task, the I variable into the task, in which I here is modified. But if the final expression evaluates to true, that will not happen because the data regions then will be merged, just the other way around, and then you would have a different value of when the data regions would not be merged. So it's an expert feature which can give you good performance if you know when and where to use it in recursive algorithms, but be careful with it. However, to be honest, currently no OpenMP implementation has any implementation for that. And finally, we have mergeable, which instructs the OpenMP compiler and then the runtime and gives it the implementation that the data environment can be merged with the outer enclosing task data environment, and that can lead to performance improvements, particularly again with recursive algorithms. I think that's what I prepared for today. That was a really quick rundown about all task-related stuff thank you for your attention. I think I'm available for questions now, if you have any. Thank you. Any questions? No questions. You have a question, go for it.